Alrighty, we are back. This is Calc 1. We are looking at 5.1, Chapter 5. We're on page 9 of the notes packet. We are approximating area. So we have the summation sign here. There's a blank. It says I is equal to what? That is called the index of summation. A sub I is the ith term. I know that's kind of weird, huh? The ith term. And then this guy, that is the summation sign. That means add all the elements together. I is the kind of the start value, and then on the top, n is kind of the end value, and we'll say f of I. That would be a function if you want to do each one. So here, let's look at sum up the following. So a little bit of busy work here. I is 1 to 8 of just I. So I just put in 1 plus 2 plus 3, I for integer, right? So the whole numbers, positive whole numbers, positive, negative whole numbers also, but they started with positive 1. So 1, 2, 3, 4, 5, 6, 7, 8. And then you add all those up, and you end up with 36. Or, there is another way to do this. I want to say there's a story about Einstein where his teacher wanted to give his elementary students busy work. So he said add up the first 100 counting numbers, and Einstein figured this out lickety-split and did it in just a couple of, less than a minute, and got yelled at for it or something because he wasn't doing what he was told to do. Sometimes brilliance is always met with open arms. So this would work too. Look, if you take 8 and 8 plus 1, 9, 8 times 9, and then divide it by 2 and multiply those and divide by 2, and you'll get 36. And he figured that out. I want to say it was something like this. If you can look at it, I'm no Einstein, but look, that's 9. And that's 9, and that's 9, and that's 9. And so it ends up being 9 times 4, but why you take n, whatever n was, if you cut it in half, because you're grouping them together. So it's always going to be half, n is always going to be halved. So this formula, instead of looking like this, might be better if you looked at it like that. And since you started with 1, you know, that would work every time. Anytime you were just summing up numbers. Now, on the next example, on B, we can't do a little shortcut. That just works for 1 to whatever. Like the one, and again, it was in one of my Einstein books. It was about his life. He wrote a couple of books. They're not easy reads, but it was about his life. And I want to say, I think it was elementary teacher, and it was add 1 to 100 or something like that. And he put together that formula, lickety-split. Got the answer. All right, let's take a look at this one. Yeah, we can't shortcut that or anything because we got to sub this 2 in every place where we see an I. So I mean, you can do it here since it's notes. I'll show you. You know, it's I equals 2, I equals 3, I equals 4, I equals 5. Thank goodness it's only from 2 to 5. And now we're doing 2 plus 1 times 2 minus 3 plus 2 plus 1, 3 plus 1, so 3 plus 1. And 3 minus 3 plus 4 plus 1 plus 3 plus 5 plus 1, 5 plus 3. All right, so those 4. So this is 3 times negative 1. This is 4 times 0. This is 5 times 1. And this is 6 times 2. So we got negative 3 plus 0 plus 5 plus 12. And that ends up to be 14. So no shortcut on that. You have to kind of do that one. But there are summation formulas. So let's take a look at those. And so these were developed. Now note, all of them go from 1 to n. So these only work if you're going from 1 to n. So if they pick up at 2 or 5 or 12 or something, you can't really use these formulas. Or you could maybe use the formula twice. It depends on how much work it would be. You could use, 1 to whatever the value is they started at and find that, and then do 1 to the end and find that and subtract them, I guess. But that might be more work than just plug and chug like what we just did there. All right, so let's see, what do we got here? We've got, if it's a constant, if you got I equals 1 to n, and it's just some number like 5 or 8 or something, you just multiply the two numbers. You just take n times c, where c is a constant term. All right. The next one, 2. We just did that. That's I from 1 to n, and then I will equal n times n plus 1 all over 2, or the iteration I put, or this is more likely what we're going to use just for simplicity, like distribute the n. So n squared plus n all divided by 2. 3. If you have it I squared, and that's n times n plus 1 times 2n plus 1 all over 6. So it's a little more complicated, but and again, if you multiply all that out, we'll see this later in the note packet here, where when we have something squared that's doing the summation, we're just going to do 2n to the third plus 3n squared plus n all over 6. So you're going to see this pop up, and we're just going to put in the n number on the top and just throw it in there. Sometimes that's easier. Sometimes this is easier. It depends on the numbers they give you. Because this might be easier. If I didn't have a calculator, I'd want to do it this way. If I had a calculator, I'd just do it that way. Just sub them in there. But without a calculator, this might be the easier way to go. Because 7 to the third isn't jumping out at me. 7 squared 49, but then I got to triple it and add 7. If I throw 7 here, it's 7 times 8, which I can do in my head. And then 14 plus 1 is 15. So, it's still multiplying, I guess. But either way, we get the same thing. 4. We got I to 1 to n of I to the third power, I cubed, and that busts down to n squared, n plus 1, quantity squared, all over 4. Or if you multiply that out, if you foil that and then distribute the n squared, you end up with n4 plus 2n3 plus n squared all over 4. Either one of those is fine for the substitution. So then the first 100 counting numbers added together is what? And so see, there's that Einstein thing. Albert wrote down 5,050 and slammed his pencil down. Got yelled at. Being too smart. So n is 100, so what does that look like? That's 100 times 101, all divided by 2, so 50. Times 101, so right, 50 times 100 is 5,000, and then 50 times 1 is 50, and then add 5,000 to 50, and you get 5,050. No and, 5,050, don't say and. And signifies a decimal point. All right, so what are we doing next? 2i squared plus 6i minus 1 from 1 to 50. Ugh, we don't want to do that all 1, 2, 3, 4, 5 all the way up to 50. Oh, here's an idea. You can do this little trick. You can split it. Split it up. Here we go. Check it out. We got I from 1 to 50, and I sure don't want to sub in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 all the way up to 50 and then add them all up. That's just begging for a mistake. What I can do is split these all up into individual summations. So this is I from 1 to 50. I'll pull that 2 out front and then say I squared plus summation. We'll pull that 6 out front and then say I from 1 to 50. I plus, or minus, I guess minus I 1 to 50 of just 1. Okay, so this is going to be 2 times, and now we can take that 50 and just put it into our equation right above for I squared. Yeah, it's probably easier just putting it into n. It's n times n plus 1 times 2n plus 1. So let's write that and then divide it by 6. Okay. So we got 2 divided by 6. I'm just doing this one for 50, so n equals 50. So we got 50 times 51 times 101. No and, don't say and unless there's a decimal point. It's not 101. In England, they always do that. Don't do that. It's 101. All right, so bloop, we multiply that out. I guess we could simplify this down a little bit and just multiply the leftovers. Like you could take the 2 into the 6 3 times, and you could take the 3 into the 51 17 times, and then just do that. It's still a pretty big number to do in your head. 85,850. I definitely did not do that in my head. I had it written down there. All right, so this one will be a little easier. 6 times, we're going to do just I, which is n times n plus 1, so 50 times 51, all divided by 2. So that's a little easier, but still, that's not a walk in the park. So 2 goes into 6 3 times. So 150 times 51, that's 7650. This one we could definitely do in our head. That's just 50 times 1. It's n times whatever the constant is, so minus 50. So we take 50 off of that, 7,600, add it on to 85,000. That's 93,450. Wasn't that a delight? All right. What are we doing here? I plus 1 over n squared is equal to n plus 3 over 2n. Yeah, and we could work that out. I'm not. You split them up, you do the individual i's, and just leave it in terms of n and I. And then put in simpler terms. And it works out to be n plus 3. So that's a proof. We don't need to do that. So for the bottom of page 9, we'll just plug these in and see what it's going to, and we'll confirm it by doing that thing. So you could basically abstractly bust down these numbers. If you're really interested in the process, at the end when I flip through all the notes, you can freeze frame it. I have it scratched out in the bottom, but it's not essential that you know how to do that. Okay, so we're just looking at what is it going to here. 13/20ths is 0.65. You go to 100, that's 103. 200ths, that's 0.515. And 1,000, that's 1,003 over 2,000. That's 0.5015. And again, you could say, okay, if this were going infinitely large, what would it be approaching? And you can kind of see the writing on the wall. It's not so obvious here, 13/20ths, but it gets a lot more obvious with 103 200ths, 1,003 2,000ths, right? 10,003 20,000ths. It's going to 1/2, right? That little plus 3 doesn't do much. So we played around with that in chapter 4, where we had the limit as n approached infinity. Okay, so let's look at page 10. Find the area under a graph, but above the x-axis. So that's what they mean by non-negative. So on the very top, it says an overview of the area problem. It's continuous and non-negative. That means at or above the x-axis, and from this interval. So let's fill in our little lines here. We got the change in x. That's going to be b minus a over n. The point where the rectangle reaches the function is then f of m or f of big M. Big M. So f of big M, that would be an overestimate. F of m, that would be an underestimate. And you'll see what's going on here when we draw the pretty picture here. Yeah, I think I might want the board for this, whole board. So this is approximation for finding area under the curve. That is the basis of calculus, is finding the exact area under a curve. So this was a way of how they did it in the olden times. So what do we want here? 10. It looks like I have C9, A, B. So here, this is A, this is B. And we're going to go with 10 lines. Oh boy. I'm bad at drawing here. 1, 2, 3, 4, 5, 6, 7. Oh, wait, there's more after this. Hold on. Thank goodness there's more after this. 8, 9. So you gotta use your imagination a little there. But that should be 10 marks, right? C1, C2, C3, C4, C5, C6, C7, C8, C9, C10. All right. And then each one of these little guys in the middle is the change in X. And so that's going to be uniform. All of these are going to be like the change in X. Each little individual thing there. But now, if I go up, look, C1, if I put that in, that hits right there on the curve. That's F of C1. But now look, this is an overestimate because it's above the curve. I get all this extra area above the curve. All right, so this is going to be an overestimate. I go up to there, but then I make a rectangle go across the top, and then all this extra area, that's F of C2, and that's F of C3. F of C4 is pretty close. And now that's all overestimate. So all this half is F with the big M. That's an overestimate. It's going to be too big. And then going the other way after that, here, C5 goes to here, and now I'm getting underestimates. F of C5, F of C6. So see, I'm missing all this area is out. So kind of hoping that this area kind of makes up for those areas. But these are all going to be underestimates. F of C7, C8, F of C9. So we're back to an overestimate there. And then F of C10, that's going to be an overestimate. So this part, this little part, is underestimate. F of M, underestimate of the areas. And then we want the limit as n approaches infinity of a sub n. So what does that mean? So if I'm looking at the area here is going to be L1 W1 plus L2 W2 plus L3 W3 plus L10 W10. The thing is, though, the widths are all the same. They're all the same widths on the bottom. So I could pull that out as a width. So the area is approximately the width, which all W1, W2, W3, all of these, W1, W2, W3, those are all the same. And then it's L1 plus L2 plus L3. So that's this length, this length, this length. I'm going to add all those up. So if I just add these lengths up and then multiply them by W, I'll get an approximation for the area. Instead of doing it, over and over and over again. And that is the change in X. Okie dokie artichoke. So let's look. It says use the rectangular method and then use actual values. So let's look at top of page 11. And we'll put this into action. Action. So what is that going to look like? It looks like they want me to find area under the curve of a parabola. And it says use the interval, so that f of x is x squared. And they want the interval from 0 to 1. And we divide 0 to 1 into n equals 5. So 5 sub-intervals. So what does that mean? That means this is A, there's 1, that is B. And now we want 5 sub-intervals, so 4 lines. 1, 2, 3, ish. So it's gonna be an overestimate here, right? So this is 1/5, this is 2/5, this is 3/5, this is 4/5, this guy is 5/5. Each length is 1/5 in between. So they're all 1/5, 1/5, 1/5. All these little guys are 1/5, 1/5, 1/5. And all I did was just kept adding 1 to the numerator. I left the denominator the same. 5/5 obviously 1. All right, and that guy's 0. 0 didn't come into play here though. So when I want the change in x, so that's all typed out already on your notes. But now let's add 1 minus 0 over 5. That's how we got the 1/5. So we got that all marked in there. So the subintervals, it's A plus, let's take a look at what that is for 2. It says the subintervals is what? It's A plus I times the change in x. So that is the starting point plus I change in x. So in this case, A is 0, the change in x is 1/5. So I got 0 plus 1 times 1/5, which is 1/5. I got 0 plus 2 times 1/5, which is 2/5. I got 0 plus 3 times 1/5, which is 3/5. 4/5. And 5/5. All right, and so now what are we going to do? So how do we find the approximate area? Let's put that. I'm going to need the board, so I got to get rid of my pretty drawing. Hopefully you got the pretty drawing. So what that looks like is the area is going to equal 1/5 squared plus 2/5 squared plus 3/5 squared plus 4/5 squared plus 5/5 squared, all times. So add all those up and then times it by the width, which is 1/5. And so what do we end up with? Oh, I see. Okay, so let's do this. Instead of making it 1/25 and 4/25 and 9/25, let's do this. Let's put the 1/5 in the front, and then let's factor out 1/25. And then you just got 1 squared, 1, 2 squared, 4, 3 squared, 9, 4 squared, 16, 5 squared. That's easier. So the 1/5 is still there. This is going to be 1/25, 4/25, 9/25. So just pull the 1/25 out and then just do the numbers. That's easier. So then what do we got? We got, add those up. That adds up to 55. Okay. 25, 55. Times 1/5 times 1/5. And then we can take that 5 into there 11 times and then just say 11 twenty-fifths. So that is my approximate area, is 11 25ths square units. They didn't tell me what it's in. Now, the reason it's approximation sign isn't because of the fraction, it's because the rectangles they're a little sloppy, right? That's not exact. So the approximation to the area under the curve from 0 to 1 is, the key idea is we need more rectangles in the same area in order to get a more accurate approximation. So how do we streamline that? The key idea, more rectangles in the same area means more accuracy. So if I changed n from 5 to 25, I had 25 little rectangles in there, there'd still be a little bit, it'd still be an overestimate, but it'd be much closer because there'd just be these tiny little areas going over that curve. And if I made n 100, I'd be right on the money. It'd be a lot closer. So increase accuracy as I increase n. All right, what do they want me to do on this page 12? Approximate area under the curve for y equals x to the third from 0 to 2 using a right and left endpoint. Okay, so the right and left endpoint, that's the overestimate and the underestimate. Try to demo what's going on there. So when we look at a third degree curve, that's one of these guys that kind of goes like that. But we're only interested in 0 to 2. All right, and n equals 4. Okay, so if we do what we just did last time, that would be overestimates 1, 2, 3. All right, so that would be the right endpoint, is what I just drew here. And so what that would look like here, if I think of this, if I zoomed in on that, 1/2, 1, 3/2, 2, and there'd be little 1/2 jobbers in between each one, like that. So that's a zoom in right there. Whoop, zoom in. You just went whoop with your hands, and there it is on the board. All right, so the right endpoint version is going to be this. It's going to be 1/2 times f of 1/2. I'm going to actually start with this one, plus f of 1 plus f of 1.5 or 3/2 plus f of 2. So that is 1/2 times 1/8 plus 8/8 plus 27/8 plus 69/8, which is 100/8 times 1/2. So it's 50 divided by 8, so 6.25. So that is the right endpoint. That is an overestimate. Let's look at a left endpoint. What is that going to be? That's going to be the same guy from 0 to 2, only this time I'm starting with the left endpoint. And so I start at 0, and then I go 0, then I go to 1 half, and then 3 halves. And I don't take it up to 2. So I start with 0. And so this one, so it's an underestimate. It's this, and this. This one was 1, 2, 3, 4 of those. This one, it's kind of 1, 2, 3. There should be 4. What did I do here? I missed 1. No. So this counts as 1, this bottom feeder, and then that's 1, 2, 3, 4. And so it's still 4, but it's an underestimate. It's a left endpoint. And so what that's going to look like is 1 half times 0. It's here, 1 half. F of 0, F of 1 half, F of 1, and F of 3 halves. So we never get that F of 2 in there. So we got 0 plus 1/8 plus 1 plus 27/8. And then I add those up. And so that ends up to be 1 half times, what is that? 8, 35, 36 eighths. Or 18 eighths, 2 1/4. So, right? Quite a difference between the left endpoint version and the right endpoint version, but also not a lot of accuracy here. It's only 4, n equals 4. That is not much accuracy. So your textbook uses upper sums, f of capital M1, which are circumscribed rectangles with a yield over the approximation, and lower sums, they say lower sums instead of right endpoints and left endpoints. So if you're doing it on the XYZ book, they're going to call this a lower sum and this a upper sum. Okay. Excellent. That is all for 5.1.